That's just the way it is. Okay, here's another example. In this case, we're going to take the region, actually it's two regions kind of, but so on the interval from 0 to 3, we're going to take the region bounded above by the parabola and below by the x-axis, and we're going to spin it around the x-axis and find the volume of the solid that we get. So first let's try to think about what this thing will look like. What do you think it'll look like? So kind of like a, I don't know, like a mod 60s kind of table turned upside down. This part here is this part, and then the bigger part here is what I've sketched in as the base. It's a pretty nice drawing, isn't it? Sarcasm. Anyway, the volume. Pi times the integral from 0 to 3, and we just need the square of the function, which is just going to look like this, right? So again, the emphasis here is on understanding the problem and coming up with the right integral. The computation, well, we still need the practice, so let's just do this one real quick. So if you make u equal to x minus 1, then du and dx are the same thing, and you can just do what I've done here. What do we get? So pi over 5 times 3 minus 1 to the 5th minus 0 minus 1 to the 5th. 3 minus 1 is 2, 2 to the 5th is 32. And negative 1 to the 5th is negative 1, but we're subtracting it, so we'll be adding it. So 33 pi over 5 is the volume of the solid. You get it? It's kind of fun. It's kind of fun to start in 2D and move it into 3D and be able to talk about volumes. Anyway, okay. Okay, now let's look at this one. We want to take the region bounded by these three curves, well, one curve and a couple of lines, and revolve it about, rotate it about the x-axis, and compute the volume of the solid that we get. So the region looks like this. And when we spin it about the x-axis, what we get is a little bit different than what we have been getting. That is, if I spin that rectangle about the x-axis, I'm not exactly going to get a disk. What am I going to get? Let's take a look. So the general picture looks like this. Now, the thing that makes the most sense to me is just to compute the volume of the outside thing, and then just subtract out the volume of the inside thing, right? So the general picture looks like this, and so the volume here's the volume of the outside thing. I subtract the volume of the inside thing, and then I'll get the volume of the outside thing with the inside thing cut out, right? And so yeah, you can totally do it like this, but since the bounds on both of the integrals are equal, and since they're both being multiplied by pi, usually we combine them into one integral and just write this like this. Okay, so the outside radius, the square of the outside radius, subtract the square of the inside radius, integrate that and multiply it by pi, and that will give you the volume. So let's apply it to the figure that we have here. So the volume here, the integral goes from 0 to 4. The outside curve is the square root, and the inside curve is 1/10 of x. And so this is the integral that gives us the volume of the thing that, that you saw in the video. But let's just compute it real quick. Right, so the antiderivative looks like this. We don't get anything when x is equal to 0, when x is equal to 4. 8 minus 64 over 3, you can do this. Finish it, please. Okay, so that's how we can handle cases where there's a hole in the middle. And actually, from here, there's a lot of places that we can go. Some of them are places you might not want to go, but for example, one of the things that we can do is to move the axis of rotation around. So instead of flipping this thing about the x-axis, we can flip it about some other axis. So what if we, instead of flipping this about the x-axis, if we flip it about the line y is equal to -1, how is that going to change things? Well, if we, first of all, what are we going to get? The thing that we'll end up with will look kind of like this, kind of, sort of. So that the hole that's up here is this hole that we'll get here. And then the base, you know, from here to here, that's this part. Okay? So how do we compute it? Well, remember when I wrote the formula before, I said we need the inside radius, square of that, the outside radius, the square of that, minus the square of the inside radius. Well, that's what we need. And so I find that when I do these things, I really use my hands a lot to say, okay, how big is the radius? So still going to multiply by pi, still going to continue this from x is 0 up to x is equal to 4. The outside radius now goes from here to here. So how far is it from here to here? Well, here's a thing that you can always use to determine the distance between this curve up here and this curve down here. You take this one and you subtract this one. Always, right? The bigger thing subtract the smaller thing gives you the distance between those two things, right? So the thing on the top is the square root of x. The thing on the bottom is -1. And if you take the square root of x and you subtract a -1, you get the square root of x plus 1, which is exactly the radius, right? Because the square root of x goes from here to here, and then to get this little bit extra, you're just adding the 1, right? You get that? So the outside radius looks like that. What's the inside radius? Well, that goes from here down to the axis of rotation. So we're going to subtract the square of that. And what is it? It's the top curve minus the bottom curve. So the integral to compute the volume of this guy looks like this. And of course, you know, you'll make those both a plus. I will reiterate that our emphasis here is on coming up with the correct integral. The computation of them, we'll either do them by hand or we'll do them on the calculator. Here I just want to talk about how to set these things up, okay? Let's try another one. I'll keep the region the same, but how about this time? Yikes! What if we revolve it around y is equal to 3? Yeah, wow. Now do you see that this is going to be the outside edge, right? Because the axis runs down the middle of the thing. So now this is the outside edge and this is the inside edge. So for this picture, the outside radius, the thing on the top, subtract the thing on the bottom. So the outside is 3, that's the thing on the top, minus 1/10 x. The inside radius runs from here to here. The thing on the top minus the thing on the bottom is 3 minus the square root of x. So the integral that gives us the volume of that thing looks like this. Okay, so the outside radius, square that, subtract the square of the inside radius, and it's always the thing on the top, subtract the thing on the bottom. It's a lot to keep track of, but that's how you do these problems. Oh yeah, by the way, this is called the washer method. Why do you think they call it that? Yeah, you're right, because when you flip a rectangle, you get a thing that looks like a washer. Okay, so yeah, if you want me to do some more examples of these kinds of things, I'm happy to do them. Just you can ask me about them in class, okay? Next, we're going to look at another method for computation of volumes of solids of revolution called the shell method.